Okay, so I apologize in advance. My dog may freak out because my neighbor is having a party. So let's first start off. I'm going to start off down here, and let's just have some kind of motion. Let's say that somebody starts off and they're running really, really fast. And then, but gradually, let's say this is a wall or something. Okay, they see the wall and they just completely slow down. And we'll say this is the positive direction, back here is the negative, just like you would expect. Okay, let me switch to the highlighter. So once they stop on the trip back, they are moving at they're speeding up and slowing down at the same rate, so they hit each one of these dots on the trip back. And I probably should have started off with one here. Anyway, actually that's extra. We'll just say that we started off here. And so let's say that this all happens in the positive. I could have started off at negative, but just for, since I get to set where things start and stop, I'm going to say that they just started at 0. So they were going fast. We just started watching them right here, and then they slowed down, and then they sped up back the other way. So like fast. We start watching them here, and then they slow, and then speed up that way. So basically, they just were running and turned around. And remember, you have to slow down and stop to turn around. If you want to prove that you can do that without stopping, let me know, because that'll be fun to watch. So anyway, let's start off first by looking at position. And why am I putting an X on this? Oh yeah, because this is vertical. This is not an X-axis, or a Y-axis or anything like that. It is a vertical axis, which represents your dependent variable. It depends on what you measure. And in this case, your position. It depends on, well, position's going to be, or your change in rather, is going to be in, that's in meters. And what does it depend on? Well, it depends on how long you watch it. How far you go? I mean, a guy could keep running. Time, which is measured in seconds. And time we don't usually write as change as, because we usually just start at 0. But position, we would kind of represent this axis as change in position, also known as displacement. This is different from distance because you see how there's a positive and negative. There's a direction to this. It's not just an amount of space. So anyway, let's look at what happens. So it would be kind of like I am sketching this. I am not plotting it, by the way. That means no grid, no little number line things on this. So let's say one increment of time, let's say 1 second, you went really far, and then gradually they start to get closer together until you come to a stop. Okay, and if you watch your moving man for too long whenever he did this, you'll know what happens next. Well, going back in the opposite direction, it's the same exact thing to where you get this, oh, that looks better than I thought it would. Good. Those are supposed to be even, but you get this kind of opposite thing here. To where basically, if you think about just having a line that just barely touches a dot on here, like a tangent line, that's going to be pretty steep. And then, well, let's think about what this tangent line represents, or what any kind of slope on this position versus time represents. Well, remember how I said this was change in position? Remember, rise over run. You wake up in the morning, then you go running, usually, unless you're a zombie, which you should not be, according to the poster. Anyway, so this would be your change in position over change in time. And just kind of an FYI, change in time for this part of physics is just going to be represented as t, because this would be when time final minus time initial. When you start measuring at 0, that goes away, and so you just write it as just time. So that's where that comes from. So that's why we're not doing change in for your horizontal axis. Anyway, so what is this change in position over change in time? Well, let's look at it. You're changing your position. See here, you're changing your position, and as time goes on, you're changing your position in smaller amounts until you stop. Back the other way, you're changing your position in greater amounts. Now think about it, how you get your car to do that, or what do you change in your car whenever you're making it go greater and smaller amounts? What thing is it that you're changing? Your speedometer, or your speed. But since this has a direction, because this is displacement, this is called velocity. Another way to look at this, if you're more comfortable with the units, I am not going to say I have a change in meters over change in seconds, but I could just look at meters per second and be like, hey, that looks familiar. Oh yeah, that's what you measure velocity in. So in that way, your units can give you a clue. So this is change in position over change in time. That is your slope. Okay, now what would happen if we took this velocity? Let's do this. Let's take this velocity and let's move it over here. Okay, I want to graph velocity, as we'd say velocity versus time, or velocity as a function of time. And look, I'm putting my units in the parentheses, not mixing those up. And velocity, if you remember, is measured in meters over seconds. So I'm going to write this, meters over seconds. Okay, and so let's see what the slope of this would look like on this. And think about your slope, like I was saying, is a line that's just kind of tangent to each one of these. If it's a straight line, that's easy, it's a straight line, but you don't get lucky enough to deal with those all of a sudden. So like, see, at first, your velocity is going really, really positive, right? You've got an extremely positive velocity. But, so we know that it's going to start off, remember this is positive up here, negative up here. You know, let me say right here, we got an extremely positive velocity. I'm just going to start it off right here. Okay, and then, whoops, as you go, time goes on, I'm going to draw a line tangent to this point. It's maybe not so much, so I'm going to do something right here, just kind of put a tiny mark so I can draw my line. And then it's getting to be like really not a lot. It is going slowly. So like maybe right here until such a time that it is, look, see when this is flat? That means that your position is not changing. So that means it is 0. So that's where it would cross this axis, because see, this is where velocity equals 0. Now, let's see what would happen then. Now I'm going to go in the opposite direction. See, the direction of my slope, that's what's dictating positive or negative velocity. This one's supposed to look like this line right here. It's really messy, but it's going to be pretty much the same amount, but in the opposite direction. I did the same thing. I'm kind of running out of graph here. I did that too big, but this should be a straight line. It will not be a straight line with me drawing it on here, but that is better than I thought it would be. And that's okay if I sketch this. I would maybe write straight line on it if I were taking an AP test, but this is your velocity. And what this says is, say your velocity is negative, slowing down, slowing down, slowing down. Oops, stopped when you cross this axis. And then speeding up, speeding up, speeding up in the opposite direction. Because look, the magnitude, the numbers are getting, if you had numbers, are getting bigger here. And that is your velocity versus time. So let's look at this. Well, next one would be acceleration versus time. Again, time in seconds. Ooh, that's really bad. Well, that's parentheses. And let's go back and look at the slope really quickly of your acceleration versus time. I mean, I'm sorry, of your velocity versus time. Well, we got change in velocity. Slope. Change in velocity over, and you don't have to draw the arrow, it's just a good idea to. You'll kind of figure out if it has an arrow or not by the context. See, as it changing, that kind of implies that it's going to be a vector. Change in velocity over change in time. Usually you'll just see that written as time. It's just a habit for me to write change in. And that's going to equal, well, if you're not sure about that, this is how fast you're speeding up or slowing down and in what direction. Think about what you'd press in your car to make that happen. The gas pedal, also known as the accelerator. And acceleration is a vector because it definitely has a direction. Now up here, let's look at the units for that. We're going to have meters per second, and let's see, times seconds. And I'm going to write seconds over 1. You know what, those parentheses are awful. Let's do something better. That's too much parentheses. How about if I just did meters over seconds, and another way I'm showing you the railroad track thing, meters over seconds, because this is where they came from, and then let's just call that a parentheses. Lazy man's parentheses. All right, and I know I want to, this is going to be my slope. I shouldn't have done multiplied just then. This is going to be my slope. I want to divide. Okay, see this line? This means divide. Division goes in the bottom. If I want to divide by something, it would go in the bottom part, because I'm kind of like cutting it in half. If it were, you know, 2 pieces, cutting it up, how many pieces like that? If I were going to multiply, go on top. So I want to do rise over run on this, so velocity over time. I'm going to put that in the bottom, and there's like an implied one up there. So this would be meters over, and seconds times seconds is seconds squared. So meters over seconds squared are the units for your slope, which is acceleration. So let me write this in green. Okay. So acceleration is measured in meters per second squared, or how many meters per second you are, how much faster essentially, and in what direction you are getting faster or slower. And then this is ugly, sorry. That's my time measured in seconds. Now if you put these over each other, you get something called jerk, but you really need, it's kind of like if you get whiplash at a car or someone slams on their brake, and that would be something you need calculus to figure out. So, oh, also notice, see this acceleration? It goes right here. I'm just graphing it. See, so you got that goes there, that goes there. So meters per second squared. And look, the slope of this thing is pretty consistent in the negative direction. So, oh, this needs to be a straight line, and it's just not going to be. But this should be a straight line in the negative part of my graph. Okay, that is what that is. And this all, just wanted to let you know, would take place in the same amount of time. So I've kind of drawn some of these over. These are not to scale. So that would take place in the same amount of time. Now, we've kind of covered the slopes. Now let's look at the area. And let's start off with the one we just did. Okay, so area on this thing, that says area, would be like, and it doesn't matter the shape, it would just be what's represented. Wow, that is bad. I apologize. It would just be what is represented by the space in between your horizontal axis and your actual slope. So on this one, it'd be a square, nice and neat, or a rectangle square. I do know my shapes. Sorry, that would be a rectangle in between the, this is gonna be easier to show with the highlighter. That would be a rectangle in between these two things. Oh, I gotta hurry. Okay, so let's figure out how to do that. To find the area, all you would do is multiply. So we're just going to multiply acceleration times time, my two axes. Now, if you're not sure what that is, let's look at your units. Meters, and remember that means divide, that means multiply. Whoops, meters per seconds squared. Now we're going to multiply by seconds. If you're multiplying, it goes in top. If you're dividing, it goes in the bottom. All right, multiply, numerator, divide, denominator. And if you can't remember denominators on bottom, small d looks like a pair of shoes for denominator. One of my fifth graders I taught told me that. Anyway, so we'd multiply by seconds. And this is just seconds times seconds, if you recall. I'm just kidding, you don't have to split it up like this. I usually just cross out the 2 on the squared, the exponent, but we're going to get rid of one of those. Get rid of these, and hey, look, meters per second for your units. What's measured in meters per second? Well, let me go back at my graphs and look. Oh, velocity. Nice. So velocity. And hey, look, this area goes back to this slope. It's really nice. So now let's look at the area between the slope and the horizontal axis on this one, which should be the same amount of time. And let's say that these two are equal in this particular case. I drew that too long. Apologize. Well, let's look and see what this one is. Okay, so now let's look at the area of the blue one, which is your velocity versus time. So it's velocity times time. And, well, we can look at the units on that too down here. Meters per second times seconds. And hey, the S's cross out, and that's meters. And guess what this slope is? Well, or not slope, I'm sorry, guess what this area is? It is your position, or change in position. And that's how they're all related.